motion of bodies connected over inextensible string. In this case, we'll be considering two bodies of masses m1 and m2. This is the first one, this is the second one. Now, this is the string, and to every string there is always a tension on the string. Then this is pulley, movable pulley. Then if this direction is downward, the tension will be towards the direction. And since there is gravity acting on this body m2, we have m2g, and the tension on the string we opposite. The tension that we have here and the one that we have here are the same. Now, if this body is moving towards the direction, it means that frictional force will oppose the movement. Now, we want to look at two cases here. The first case is when the body m1, or the motion of the body, is at equilibrium. That is, when the coefficient of static friction is equal to 0. When the bodies are at rest, when m1 and m2, when they are not moving. Then we need to consider when they are in motion. Now, let's see when the body is at equilibrium. At equilibrium, that is, when the coefficient of static friction between this surface and body m1 is equal to 0, it means that there's going to be a reaction from this body. A reaction which is normal to the plane and the weight of the body, m1g. This is m1. At equilibrium, we have the tension is equal to the frictional force. Normal reaction is equal to m1g. Let's take note of these two equations. When the coefficient of static friction between the bodies is equal to 0, it means that the tension is equal to the tension applied here is equal to the frictional force. That is, the total horizontal forces are equal, while the total upward and downward forces are also equal. When in motion, when the bodies are in motion, when the bodies are in motion, that is, when the coefficient of static friction is not equal to 0. You now look at it. The motion is towards the direction. That means the tension here is greater than the frictional force. We now have this way. The tension T minus frictional force is equal to the resultant force, which is M1A, equation 1. Considering the mass M2, the weight of the body is vertically downward and the direction of motion is downward, which means this weight is greater than this tension. We now have M2G minus the tension is equal to M2A. This is equation 2. Now, solving equations 1 and 2 simultaneously, we can add equation 1 and 2. 1 plus equation 2. If you sum the two equations together, we see that the tension will cancel each other. Therefore, M2G minus frictional force is equal to M2A plus M1A. M2G minus frictional force is equal to, acceleration is common, let's factorize it, plus M1, close the bracket. But frictional force is equal to coefficient of static friction multiplied by normal reaction. It means that this equation becomes m2g minus, if you substitute this into this equation, we now have normal reaction multiplied by coefficient of static friction, which is equal to A multiplied by m2 plus m1. Let's make the acceleration subject to the formula. We divide both sides by m2 plus m1 divided by m2 plus m1. Can call this equation 3. Equation 3. If you look at when the body is at equilibrium, we see that m1 or weight, which is m1g, is equal to the normal reaction. We can substitute normal reaction into this equation 3. So we now say substitute normal reaction in equation 3. Normal reaction is equal to m1g, and equation 3 is acceleration equals to m2g minus coefficient of static friction multiplied by normal reaction over m2 plus m1. Now let's substitute this into this formula. Acceleration will now be m2g minus coefficient of static friction m1g divided by m2 plus m1. If you look at the numerator of the equation, g is common. We can factorize g. That will be m2 minus coefficient of static friction multiplied by m1 over m2 plus m1. This is equation 4. Equation 4. This equation can also be used to determine the acceleration when the coefficient of static friction is not equal to 0. Now, taking the coefficient of static friction equal to 0, if you substitute this into this equation, acceleration will now be g multiplied by m2 minus 0 times m1, everything divided by m2 plus m1. Therefore, acceleration will now be g, everything here is going to be 0. m2 minus 0 will give us m2. So g multiplied by m2 divided by m2 plus m1. So this is equation 5. Equation 5. This equation can also be used to determine the acceleration when there is no coefficient of static friction or when there is no frictional force. When the coefficient of static friction is equal to 0. If the coefficient of static friction is equal to 0, there is no frictional force. So equation 5, equation 4 can be used to calculate or determine the acceleration of the body. Now, at the initial position, when the acceleration of the body is equal to 0, we can determine the coefficient of static friction from equation 4. Equation 4 is acceleration equals to g times m2 minus coefficient of static friction times m1 divided by m2 plus m1. This is equation 4. So if acceleration is equal to 0, this implies that everything that we have here is equal to 0. G multiplied by m2 minus coefficient of static friction times m1 over m2 plus m1 equals to 0. If you cross multiply, you see that g m2 minus coefficient of static friction m1 will give us 0, because everything here multiplied by 0 is going to give us 0. If you now divide both sides by g, g will remove g. Now m2 M2 minus coefficient of static friction M1 is going to give us 0, because 0 over G is defined. That is going to give us 0. Therefore, coefficient of static friction M1 is equal to M2. If you divide both sides by M1 will remove M1. So coefficient of static friction will now equals to M2 over M1. So we can use this equation, let's call it equation 6, to determine the coefficient of static friction if it is required to calculate.